think of this as a coin, right? The coin gives heads, means that this particular experiment, random experiment, in this particular random experiment, k-means plus plus has given an order 1 approximation. Coins gives tails, which means that in this particular experiment or initialization, k-means plus plus has not done so well. The probability of head is at least half. Okay, and now I take the minimum over 10 runs. What is the probability I'll get at least? I mean, what is the probability I'll get order 1 approximation is the same as what is the probability there'll be at least one head? 1 minus 1 by 2 to the 10. Right? Because the probability that none of them give you heads, probability that in all the 10 runs, k-means plus plus performs really badly, is at most half, half times half times half 10 times, 1 over 2 to the 10. And because I'm taking the minimum, right, probability that at least one of these runs is a order 1 approximation is 1 minus 1 by 2 to the 10. Because it does well in one of them, I'm going to take that because I'm taking the minimum of the solutions, right? So this is like 0.999, right? Which is amazing. So sort of, I mean, you just run it 10 times. Okay. In practice, we'll just run it once though, and that will be good enough. Okay. Okay. So let's look at this. What is the runtime for k-means plus plus? So there's the number of iterations. Which I'll tell you that it's a constant. In practice, you will see that it's about 10. But what is the runtime in each iteration? Time per iteration. And what is the cost of initialization? This you do only once. So time per iteration, we have done this, right? And this remains same, nkd, because after you initialize, you're just running Lloyd. So this remains same. What is the initialization cost here? Because initialization is tricky. We choose a point, we choose the first center uniformly at random. For the next center, we find out the distance of every point from the first center. We create this probability distribution. We sample from this probability distribution. That gives me the second center. Then we choose the third center. Then for choosing the third center, I again do this, find out dx from every point, right? And then find out the distribution, sample from the distribution, and so on. So then what is the time for this? So let's say we have chosen k minus 1 centers already. Now for every point, we compare with each of the centers in times order d times k, and that gives me the d of x for x. And so the d of x for all of x is n times kd. Yeah. And sample, and then we keep on sampling, right? And we do this for k number of steps. So nkd times k, right? Because for every center we have to do this. For choosing every center we have to do this. So the time for initialization is order n k square d. Which now it starts looking a little tricky. Because n k square d, okay. We'll see how it really does in practice. So here is some plot that I kind of took from this Sergei and Vasilievsky's talk, right? So what is this? This is, think of the x-axis as the stage of the number of iterations. And y-axis as the k-means cost. Right? So the y-axis should go down as I kind of increase as I kind of do more and more iterations. So you see that this is the Lloyd. The blue one is the Lloyd. Right? The red one is some hybrid. I don't know what it is clearly. And the green one is the k-means. Right? That clearly does well in practice. And I think the data set is something that is, if I remember, it's like the 20 news groups data, which is a pretty big data set. So this is the kind of plot that we'll try to produce also. Okay. Okay, so now, then the next question is this, that assume, okay, all this is nice, but now look at this, that, okay, what do we have? We have a nkd times number of iterations, okay? You guys are all budding data scientists, so you're not going to work with small n and small d, right? I mean, think of the, let's say an English corpus where n is 1 million. Number of words in the English dictionary is about 100K or something, maybe 50K. You include all bigrams and so on, right? So nkd and k is like, let's say you have put k to be 1000. Sorry. So this is huge, even per iteration, right? So this is not, I mean, this is not really that scalable for on a single machine, right? If the data happens to be large, right? And this we can see. So what can we do? What can we do to sort of scale this up? One way to scale this up is to use this multiple machines, right? And we'll use this multiple machines. So using multiple machines is not trivial, right? Because if you remember that we have to do this iterative thing, right? We have to say, find the centers, assign the points, find the centers, and so on. So how will we do this, right? Because when you have the data distributed on multiple machines, without going into too much details of the actual sort of computing platform, when the data is distributed across multiple machines, communication is a big headache. So you don't want to be communicating too much data across machines, right? But I mean, that's precisely what a naive implementation of this has to do. So what is an intelligent way of sort of parallelizing this when you have the data distributed across across a number of machines? So here is what we'll try to do, right? What we'll try to do is try to partition the data. Okay? So think of these as multiple machines. So each of them, I don't know if it looks like a desktop, but each of them is a workstation. So this is what we have, right? And now what we say that partition the data, give everybody their own set of points, okay? And now let them work. Let them sort of do a k-means on that set of points. Now what would you do?
So how many clusters?
Some number. Depends on what is your budget. Give me a budget, I'll tell you how many machines here, or how many clusters? How many clusters is also a parameter. So let's say overall you need to do some k clusters. I don't know how many, but let's say k potentially is much less than number of machines, or maybe even bigger. I don't know. Actually, let's not make this assumption. There is some number of clusters that you have to do.
So like when we need 20 clusters, then machine 1 will cluster 5, machine 2 will do the next.
But how? So the naive way of thinking about it, the first way of thinking about it, I shouldn't call it naive, is that can machine 1 create cluster 1? Can machine 2 create cluster 3? Can we do this? I see some vigorous nodding, so why not?
Like all the systems will cluster the data for all the, it will each cluster for 20 things.
Because I don't know the clusters a priori. So I don't know which data to give to machine 1 in order to create the cluster 1. Right? If I had known that, then my problem would have been solved, right? So initially, I mean, I cannot say that machine 1, you go and create cluster 1. Because who knows? The cluster 1, I mean, the data is just some big file. Cluster 1 could come from here, from different parts of this file. So how would I divide up this data? All I can do is arbitrarily partition the data, right? So that may partition the clusters, and each cluster might be each machine can potentially have representation from all the k clusters. No. We're talking distributed. So let's say, so I'm not giving you the entire terminology, but you guys must have heard about Hadoop, MapReduce, Spark. So let's say we're talking in that setting, Right? And this is actually an algorithm in that setting, that in that case, the data is distributed across multiple machines. So one machine has let's say we're talking about logs. One machine has today's data, another machine has tomorrow's data, third this machine has this data, and we have to cluster across all of this. So what is the natural way? And I'm citing you on because I think you guys can come up with it. This is a very natural algorithm.
So what if we like if you have 5 machines, on a first computer just make 5 clusters.
On a first computer, make 5 clusters.
Assign each cluster to each machine for further clustering.
Assign each cluster to each machine. So I don't know what that means.
Like if I have an entire 1 million data points, I cluster them into say 1,000 points.
How do I cluster them? That is the first question, right?
They're playing k-means, like just 5 normal k-means on one machine. I get big clusters, that cluster may itself have smaller clusters inside it.
I see. So okay. So let me rephrase what is being talked about. So suppose we are saying that, okay, we have like 10 million points and I want 10,000 clusters. Instead, what you are saying, okay, let us not think about 10,000 clusters right now. Let us think about 10 clusters right now, right? Let us do 10 clusters of 10 clustering of the data point. Maybe you can do it on a single machine. I don't know. Maybe you can. But suppose you can, right? Then you sort of do this rough clustering of the data. Then you send off the first cluster to the first machine, second cluster to the second machine, and so on. Right? That's what you're saying, right? And the first cluster will then try to refine the first machine will try to refine the first cluster into 100 clusters. And if you do that for each of the 10, you'll get 100 times 10, 1,000 clusters overall. Is that an accurate representation? You're saying something about this? So,
But there'll be overlap between the...
So as of now, there's no overlap. If I assume correctly, maybe you're thinking about doing this. So doing this partitioning overall, and this goes to machine 1, this part goes to machine 2, this part goes to machine 3, and then machine 1 further clusters inside this. Machine 2 further clusters inside this, and so on. This is what is being said. So this is not bad. Assuming you can do the first clustering in a single machine, right? Assuming you can do this, this is not a bad idea. In fact, this is a very well-known algorithm. It's known as Canopy clustering. Right? So in some sense, the first clustering, approximate rough clustering, rough partitioning of the data, think of it as a canopy. You put it under 5 canopies, and then inside there you do this small clustering. However, the problem is that you have to solve the first big clustering. You have to solve this 1 million, and even that might not be possible. So we'll try to do this. How to do this? So we have, as we said, we have partitioned the data into multiple machines. So then let us take, again, the same intuition. Let each of them come up with 1,000 clusters. 1,000 clusters, k equal to 1,000. Each of them come up with 1,000 clusters. In their own machine. So suppose we do that, right? Now what do you want to do? Do what? You want to merge these clusters, right? But if you want to merge these clusters, you don't want to be sending all the data points. So what do you want to be sending? Only the centers. Very nice. You want to be sending only the centers. But you want to be sending the centers with some more information. Number of points it has. Right? Because if a center actually has a lot more points, moving that center, is going to affect a lot of these points. As in reassigning that center to somewhere is going to have that center has that much weight. Right? So precisely that is algorithm. That you first partition the data points into, let's say, p partitions, and first we calculate a clustering for each of the xi's. Right? So let's say this is the clustering. This is the clustering for the xi, right? The ci1 to cik is the clustering. Then we define the size of each cluster, okay? And then we say that okay, each machine now sends only the cluster centers, but it gives it a weight. It kind of assumes that all the other points are collapsed to this one cluster center. So now you have a number of points that is equal to k times p. P is the number of partitions, and k is the number of cluster centers initially. So only this many points, and weights on these points. This many points could be fairly small, right? If you have like, even if you are in a reasonable university, maybe you have like 1,000 machines that you have sort of sneaked up on from your advisor, and p equal to 1,000 and k equal to 1,000. This is like 1 million, nothing. 1 million. Now you put them together in a single machine, you just cluster them, right? The question is that, is this clustering any good, right? Because how do I know this clustering is any good? So then just to sort of give you a picture, then suppose there are these clusters, and then there are, I'll just maybe all of you understand, but now suppose you say that that these points go to machine 1, these points somehow go to machine 2, these points go to machine 1, these points go to machine 2. So now machine 1 does a clustering. Machine 1 has some of the purple points, some of these red points. Machine 1 does a clustering, machine 2 does a clustering, right? And then machine 1 puts in a center here, and machine 2 puts in a center here, machine 1 puts in a center here maybe, machine 2 puts in a center here, machine 1 puts in a center here with the corresponding set of weights. Now then we have only 4 points here. In the next phase we have only these 4 points which are the cluster centers with the corresponding weight. So this has weight, this thing has weight 1. So the weight is based on the number of points in this cluster. So for instance, this black point has 1, 2, 3, 4, 5. So the weight will be 5, basically. And this point will have weight 1, 2, 3, 4, 5, 6, 7, 8, 9, something. I mean, you could have said that why is this the weight? Why not take into account the radius? Why not take into account all the distances? But turns out that this works, right? In the following sense, that suppose you have two approximation algorithms, right? So there are 2 phases, right? One phase that works in each of the machines, and other phase that puts it together. But suppose you have some approximation here, you run some approximation algorithm here, some approximation algorithm here. Overall, you get something that's a function of both. So this thing is complicated. Don't worry about it. We'll sort of see what happens with k-means. Basically, what it says is that if you run k-means in each of the machines, plus finally, overall you get a log square k approximation because of this log k times log k. Right? This is what you will get. Okay? So this will be a log square k approximation. Again, it will have the same kind of properties. This is really log square k in the worst case. In practice, it performs much better. Okay? So the point to take home is that we can parallelize k-means plus plus, and so that in only 2 rounds of, I mean, just to sort of make it a little more concrete for people that you know, in only 2 rounds of MapReduce. Anyway, I haven't done that. In only 2 rounds of MapReduce, you can do the run the k-means plus plus algorithm, and it gives you a fairly good approximation, both in theory and in practice. Okay. So I was going to sort of go through the runtime, but let's skip that because we have done that for a multiple number of problems in this class. Okay. So just to summarize k-means, let's summarize k-means and move on to something else. That k-means used to be one of the algorithms in which there was practice that was working very well. Nobody could explain it. There was theory that was coming up with more and more complicated algorithms that people didn't know what to do with. They didn't work well in practice. But now the 2 things, over the last 5 years, the 2 threads have sort of very thankfully come together, and it has given a very nice research problems as well as very nice algorithms. In fact, there's also more complicated, little more sort of complicated analysis that goes beyond what is known as which is known as beyond worst case analysis. And you saw one example of that, but there are more examples of that. Some of these are known as smoothed analysis, some of these are known as average case analysis that says that no. What you see in the k-means algorithm in the worst case, that doesn't really happen in the real sort of data. It is much better than that. So before I go into hierarchical clustering, any specific question on k-means? Let's move on to hierarchy. Here's the next question, right? This is all very good, but we don't know the number of clusters. How do we come up with the number of clusters? Right? So what do we do? What do you think we do before going into hierarchical clustering? What would you do if you don't know the number of clusters? How would you guess? We have already given you one hint in terms of nicely clusterable. Check the cost. Yeah?
One equation where cost of k clusters,
And the cost of k minus 1 cluster was something.
k minus 1 that we go for.
Good point. Good point. So then we already sort of hinted upon it, that we check if I really want to guess the number of clusters, what if I check the cost of clustering with k clusters, the cost of clustering with k minus 1 clusters? Okay? See, the cost of clustering with k clusters is always going to be less than the cost of clustering with k minus 1 clusters. Why is that? Why? You nodded. Why is that? Cost of clustering with k clusters is always, optimal cost of clustering with k clusters is always at most optimal cost of clustering with k minus 1 clusters.
As we increase the number of clusters, the distance is reduced.
Intuitively, but what is the complete proof? I was actually talking about you. You also nodded very vigorously. Why is that? But anybody, sorry, I didn't want to put you in spot. Anybody else? Because here is a clustering with k centers. Take the optimum k minus 1 clustering. Put one cluster center on top of another. It's a k center solution, right? So therefore, there is already a k center solution, right, that achieves the optimum cost of the k minus 1 center. So therefore, the optimum cost of the k center can only be smaller than this, right? So therefore, it sort of goes down and down. But what you see is this following curve. That typically this is what is known as. So you'll see this called elbow curves. So you plot k. On the x-axis you have k, which is number of clusters. On the y-axis you have the cost, the optimum cost with k clusters. So obviously you can never know what is optimum cost with k clusters, but you run whatever your favorite version of k-means is with k clusters. Right? And then you see how the cost goes down. The cost will go down. There's no question. The question is that does the cost go down like this? Does the cost go down like this? Right? In most data sets, if it's really nicely clusterable, it will take this form. Right? Then you kind of say that okay, there seems to be. I mean, ideally, a lot of books show you this kind of a picture, that the cost is something like this, and suddenly there is a drop. Right? And this point is called the elbow. And because of the sudden drop. This doesn't really happen in real life, I'll tell you. This doesn't really happen in real life. Real life is not that simple. Right? You will see kind of a more smoothened cost, and you kind of say that okay, I am happy with this objective function cost. Right? And I'll choose k to be this. Right? That is one way of doing it. Another way of doing it is what will go into more advanced topics in machine learning that I won't talk about, is known as regularization. Right? So in some sense, you can think of it as a trade-off between how small you're driving the cost and how many clusters you are adding. Right? I mean, if you add more clusters, that's making your model more complex, and that will reduce the cost. So somehow there has to be a trade-off between the two. And this is done through what is known as regularization that we will see later. We won't go into that detail at all. Right? So that is actually the right way to do this. Okay? But here is what we'll do now. But I mean, somebody had a question about how to choose k. Does that more or less answer your question? Very vaguely. But here is what we'll do. What we'll do is that, Golimaro Keiko. I mean, what we'll say is that we'll produce a set of clusterings for every k. Okay, so what we'll do is that we'll sort of say that okay, you name me a k. I'll produce a structure such that you name me a k. I'll cut off that structure to give you a cluster of that size. If you want a k equal to 2, I'll cut it off appropriately so that I can derive a clustering with k equal to 2. if you want k equal to 1 million, I'll cut it off appropriately to give it k equal to 1 million. I mean, obviously k cannot be more than the number of points. So k, anything between from 1 to number of points, I'll sort of give an appropriate clustering. So this is what we'll try to do. So this is known as hierarchical clustering. Right? I mean, there's a lot of uses to this, and one very specific use that I like is in terms of recovering phylogeny. As I said, that you apply this to DNA as the data points, and then you try to say that the tree that, I mean, this will give you a tree. I mean, I sort of let that out, but we'll get a tree of, I mean, we'll create a tree, some sort of a tree. And then in phylogeny, what people do is try to say that is this tree the same as the tree of evolution? That we all came from chimps and so on, in spite of some of our ministers saying something else.